Hello and welcome back to Grade 10 Science SNC2D. In the previous lesson, we looked at everything to do with ionic compounds, ionic bonds, the properties the compounds have, how we can name them, or how we can write their chemical formula. In this lesson, we focus on a different type of compound, which are molecular compounds. So we want to demonstrate an understanding of these compounds. So what makes them different from the ionic compounds, how are they formed, and what sorts of properties do they have? So what are molecular compounds? A molecule is a combination of two or more atoms held together by covalent bonds. So notice these are now combinations that have been created by covalent bonds, not ionic bonds. A covalent bond is a connection usually between the atoms of nonmetals in which the two atoms share a pair of electrons. The electron pair belongs to both atoms, and the attraction of the atoms for the same electron pair holds them together. So in the ionic compounds lesson, we learned that an ionic bond is formed when you have two oppositely charged ions, and the force that holds them together then creates an ionic compound. So in that case, the electron from one atom completely leaves and becomes a part of another atom. The electrons aren't being shared, or it's not that the electron is jumping back and forth. It's completely gone from one atom, from the metal, and the non-metal then takes that electron and then makes it part of it permanently. With covalent bonds, instead of a full transfer of electrons from one atom to the other, the electrons actually remain in a space where both of the atoms can share them and experience them and use them at the same time. So this commonly happens between atoms of nonmetals. So when nonmetals and nonmetals are trying to bond together, it's done through covalent bonds. So because of the bonds that are involved in these compounds, naturally they will have certain properties. The first one being that they are often soft. If they dissolve in water, they form solutions that do not conduct electricity, and they tend to have relatively low melting points. So white table sugar can be melted on a stove. So unlike ionic compounds, which are able to form certain types of rigid crystals, molecular compounds are less likely to do so. They're mostly soft. They, even if they dissolve in water, will not be electrolytes. They will not be able to conduct electricity compared to something like a salt. And they tend to have relatively low melting points. So it does not take as high as a temperature to melt them. So remember with salt, the temperature was upwards of 800 degrees to melt salt. With white table sugar, the temperature does not need to be as high and can be easily melted on a stove. So what's the difference between an ionic and a covalent bond? An ionic bond involves an electron transfer from a metal to a nonmetal. The metal loses an electron to the nonmetal. Metal becomes a positive ion, nonmetal becomes a negative ion. Covalent bond involves sharing of electrons between two nonmetals. So again, here we are a bond in which there isn't a full transfer. The electrons are equally or mostly equally still part of both of the atoms that they're coming from. Next is molecular element. In a molecular element, two or more atoms, all of the same element, are joined by covalent bonds. A diatomic molecule is a molecule that is made from two atoms. For example, the element chlorine is a molecular element that exists as a diatomic molecule. So molecular element is essentially, think of it as a molecular compound that's made of the same element. So a good example of this is the Cl2 compound. Consider it a compound if it helps to see that it is just a unit in itself, and it's made up of two chlorine atoms. Now, chlorine itself is a nonmetal, so if it's trying to bond with another nonmetal like itself, it's not going to be using the electron transfer approach like it did when it was trying to bond with the sodium in the ionic compound. Here, what the two chlorines will do instead is share electrons. So the valence electron in the shell of one chlorine and the valence electron in the shell of the other chlorine will behave in a way or will overlap in a way where the electrons are able to share and be a part of those valence shells. So this in the middle here, consider that to be the sharing that is happening between the two molecules. So they each share one electron to form one pair of shared electrons. So one chlorine gives one electron, the other gives the other, and what they have is a pair between them that is being shared. The formulas for diatomic molecules contain a subscript. In the formula of a molecule, a subscript tells you the number of each atom in the molecule. So chlorine molecule is symbolized as Cl with a subscript 2, so something like this, which tells us that it's two chlorine atoms that are present together. Other non-metal elements exist as molecules too. So oxygen and nitrogen, which form 99% of the air, are also diatomic. So diatomic, think of it as two atoms, di meaning two, atomic meaning atomic. So these are elements that always exist in pairs. So oxygen, you're less likely to find as just an O and more likely to find it hanging out in pairs of diatomic oxygen or O2. And apart from that, as you can see, there are various other ones. So hydrogen, nitrogen, fluorine, bromine, iodine, all exist primarily as diatomic molecules. So they're always hanging out in pairs and are connected through the sharing of electrons. So they each are sharing a pair of electrons between themselves. Next, we look more closely at molecular compounds. So when atoms of two or more different nonmetals combine, a pure substance known as a molecular compound is formed. As with molecular elements, the atoms in molecular compounds are joined together by covalent bonds. In each bond, the atoms share a single pair of electrons. So what we just saw earlier on is molecular elements, meaning it's the same element, but more than one atom of that element bonding together. What we're looking at now is different elements, different nonmetals bonding together through covalent bonds where they're sharing electrons. So water is a molecular compound. There are two covalent bonds in water. Each hydrogen shares one pair of electrons with an oxygen atom. The other example we have here is that of hydrogen fluoride, which is made up of two different elements, hydrogen and fluorine. So here on the left is our hydrogen. Here we have the fluorine. And in the middle, you see this overlap is where the sharing is happening. So this here is the site of the covalent bond where the pair of electrons is being shared. And just like in ionic compounds, where the whole point of electron transfer was to give the atom more stability, the point or the goal of these covalent bonds is again to provide stability. Because if the atom is able to find electron from somewhere to make it or give it a full outer orbit, it will try to do that. And it's okay to do that even if it has to share the pair of electrons with another atom, because that's still more stability than not having a full orbit at all. So here are some other examples of molecular compounds. So compounds made through covalent bonds between nonmetals and nonmetals. So here we have PCCl5. So the name of this would be phosphorus pentachloride. The penta comes from the fact that there are 5 chlorines. So as we'll see, naming with molecular compounds is a little bit different than with ionic compounds. And with a lot of molecular compounds, they have more common names that they're referred to rather than the technical names. So phosphorus pentachloride is a compound which is used in the production of lithium-ion batteries. Propane, you may have heard, is often used as fuel. Sulfur dioxide is used in the production of sulfuric acid for car batteries. Tetrafluoroethylene is production of Teflon plastic. So if you have a pan which has a Teflon coating on it, the tetrafluoroethylene is part of the process of creating that coating. Acetylsalicylic acid, which is this large formula here, is a common pain control medication. And then the last one we have is ascorbic acid, which is a component of vitamin C. So molecular compounds are used all around us, have a lot of important applications associated with them, which is why we try to learn about them and understand them as well. And notice in some of them, we have more than 2 elements that are forming or creating the compound, so the last 2 down here. But again, the bonds within them, whether it's 2 elements or 3, are still covalent bonds, meaning there's sharing of electrons happening at different places where these elements or their atoms are overlapping each other. Next, we get into some naming practice for molecular compounds. So chemists have established a system for naming molecular compounds that involves using prefixes to specify the number of atoms. The prefix is attached to the name of the element to which it refers. So if you have 1 oxygen or 2 oxygen, that's dioxide. If you have 3 oxygens, that would be trioxide, and then so on. So if instead of oxygen, it's something else, you would still have the di or the tri in the front and the name of whatever that particular element is. So the number that's associated with that particular element in the chemical formula is important in coming up with its name. So for example, the name dinitrogen pentoxide tells us that there are 2 nitrogen atoms. So di meaning 2, and 5 oxygen atoms because we have pent. So dinitrogen, 2 nitrogen, pentoxide meaning 5 oxygen. So that's why we get the chemical formula of N2O5. So the crisscross method that we used in naming ionic compounds is not entirely useful. With naming molecular compounds, we more just rely on directly on the subscripts instead of switching it back and forth, and making sure that the name matches the subscripts on each element that we have within the compound. So that is the dinitrogen pentoxide chemical formula. In this table down here, we have a few others as well. So here is our chemical formula, N2O. So we have 2 nitrogens, meaning dinitrogen, and a single oxygen. So the prefix for single or 1 is mono. So this would be dinitrogen monoxide, which is what you have here. The other one we have is PBr3. So P is phosphorus. It's only a single phosphorus, so we can just say phosphorus. And then 3 bromines, meaning tribromide. So we have phosphorus tribromide. So in a lot of these, you'll find that the element term that's coming second will have a IDE ending. That's why we have pentoxide or monoxide or bromide. The prefix mono is only used for the second element in the compound. So if the first element is single, we don't need to add mono to it. It's only if the second element is alone. Similarly, the name carbon monoxide states that there is 1 carbon and 1 oxygen atom in the molecule. So we don't need to say in the front of the word carbon, we don't need to say monocarbon monoxide. Carbon monoxide will still give us the same chemical formula of CO. So here again is the prefixes that are used, and then some sample molecular compounds. So carbon monoxide of 1 of each. Carbon dioxide means 1 carbon, 2 oxygen. Sulfur trioxide is 1 sulfur, 3 oxygen. Carbon tetrachloride, so 1 carbon, 4 chlorines. And then phosphorus pentafluoride is 1 phosphorus, penta is 5. So we have the subscript of 5 on the fluorine. Some molecular compounds have common names that we often do not use their chemical names. For example, the chemical name for H2O is dihydrogen oxide, but we just call it water. So more often than not, when you see the chemical formula H2O, it can be called H2O itself or water. It's typically not referred to as its technical or chemical name, which is dihydrogen oxide. Same thing with something like NH3. This would again have a technical name of nitrogen trihydride, but it's commonly referred to as ammonia. NO would just be nitrogen monoxide, but it is commonly referred to as nitric oxide, and it's an air pollutant produced in the automobile engine when gasoline is burned. And then finally, we have hydrogen sulfide. So notice it's actually two hydrogens, so it should technically be dihydrogen sulfide, but it's commonly referred to as just hydrogen sulfide, and it is an invisible gas with a distinctive rotten eggs odor. So naming, again, all depends on the subscript directly connected or attached to the element, and then the subscript tells us what prefix to put in front of the name of that element. To end this lesson off, there are some practice problems for you to try to name some binary meaning two element molecular compounds, and then also given the name to try to come up with the chemical formula. So make sure to have the table of prefixes with you if you are not familiar with them. So you know that 3 means tri, 4 means tetra, whether you're trying to name them or write the chemical formula. And make sure to use the subscript that's directly attached to the element. So for the first one, we have SO3. So that means we have a single sulfur and 3 oxygen. So this would be sulfur trioxide. If the element in the front is just 1, we don't need to say monosulfur. We can simply say sulfur trioxide. And then a similar sort of process should help you come up with the others as well. So make sure to try out these practice problems to get familiar with molecular compound naming. You will come across various of these compounds as we move forward in this course, and with a mix of the ionic compounds that we learned in the previous lesson as well. So with that, we are brought to the end of the lesson of molecular compounds. So we learned about how different they are, first of all, from ionic compounds. We learned about covalent bonds or electron pair sharing, which is what keeps these compounds together, and that they primarily happen between nonmetal and non-metal situations. So that is it for this lesson. Thank you for listening, and I will see you in the next one.